Attempt at this. This is Mass 6620, and I've already tried to put this video up one time, had a technical glitch. So no, I'm not going to throw the baby out the bathwater. Just going to start over and do the best we can. I think I got to tell you, I'm putting this video up on a Tuesday, and I created this lecture last Thursday. So it's been 5 days, and there's a couple of things that I forgot. It caught me. So we'll do the best we can. Again, it's Math 6620. What the purpose of this video is we're going to look at, we kind of set the stage for implementing a log linear analysis. Hopefully by now you know that we can re-express chi-square as a regression model via log linear analysis. And what we want to do now is look through an example and see how we actually carry one of these out. Okay? Now recall, and I'm going to go over this again because I shut R down, but recall that in R we'll create two new variables. Well, actually it's two new data frames, I should say. And we'll use the subset function, which is a really helpful feature when we deal with categorical data. But we're going to call these just males and just females for obvious reasons. When we ran these in the previous video, we saw that we had standardized residuals in every cell that exceeded 1.96. And that just tells us that, this tells us that each cell provides significant contribution to our overall model. Okay? Now, what we'll want to do is, once we carry this out, just to give you, again, a preview or kind of an intro to the game plan, is we'll want to examine our model just across males. We'll use something called a log linear model command, and we'll see that it works similarly to the linear model that we used back in regression and the GLM that we use for logistic regression. So, guys, let's without further ado, let's make this happen. Let's go into R, and right now I see that I didn't have R up, so I should have. Okay, well, that's fine. So let's start from the beginning. I have to admit, I thought I had this going. And I got to be honest with you, I don't remember what I called the data set. It looks like it's called party, belief, gender. And of course we need to attach it. I want to go ahead and I'm pretty sure that I capitalized everything, but I just want to look at the names of the variable. Yeah, I did. So we're going to have to refer to this as capital P party and so on and so forth. Now, the first thing again I want to do is I want to create this this new data frame, and I'm going to call this just males because I'm not really creative other than that. And we'll use the subset function, and we want to use our overall data set, which we call data, but I want gender to focus in on just those that are coded as male. I want to go just females. Same way. And guys, let's go ahead and we need to look at install the library for G models, and we'll need the library for MASS. All right, so we should be ready to go. Now, when we express log linear analysis as a chi-square using R, the first thing we'll want to do is we'll want to examine our model separately for males and females, but we're not going to be able to go straightforward with this like we did previously. What we've got to do first of all is we have to create what are called contingency tables. So first we'll create contingency tables across gender. So one for males, one for females. Now, if we were doing this for a categorical variable that had three categories, then clearly we'd have to create 3 contingency tables. Okay. Now, first thing I want to do is I'm going to create just what I'm going to call a male table, and I'm going to use X tabs, and I want to run this tilde across party plus belief. But I want my data to be just males. Make sure I got that right. Yeah. Now let me show you what I created, and I didn't do anything brilliant here. Rarely do I. But what I did here in the male table is I just separated out the reliefs, or I'm sorry, the results across pro-choice and pro-life across Democrat, Republican, just for males. Okay. Now the next thing I want to do is I want to run my model. And I'm going to call this male model full, because what I want to do, I want this to be an interaction model. In other words, I want to create a saturated model here, so I'm going to call it my full. And for my terminology here, full just means we're including the highest order interaction. So guys, we're going to use log linear model, and I want to go tilde, party plus belief plus the interaction. The next thing I need to do is I need to let it know that the data I wanted to use is the contingency table, male table, and I want the fit to be true. I'll explain this in just a second. So hopefully that all happens to where we get this without an error. Now again, think of log linear model as just LM or GLM that we've used before. But the only difference is, notice that previously we would have our dependent variable in front of the tilde. Now, we don't put anything in front of the tilde here because we're not predicting anything. We're essentially predicting the frequencies for cases at different conditions or combinations of the predictors. So we're not essentially predicting anything, we're just kind of creating, if you will, the expected frequencies. Okay? Now, next thing I want to do is I want to create a male model, and I'm going to do this one as none, because I'm not going to include the intercept here. And you're going to see that this is an important to point out, because this tells us exactly. Trust me, I'm not talented enough to speak and type. The male model none. Notice what we left out. It was the interaction. The way this process is going to. Well, I'll tell you what. I'll explain the process in just a second. Okay, we'll write it down. That way there won't be any confusion. All right. Really, other than, let me explain this too. This part out here, fit equal true. What this does for us is this command obtains the expected values. So ultimately, what's going on behind the scenes here is the models that we created compare the proportions of the observed and the expected exactly like what we do in a traditional chi-square. All right. Now, next thing we want to talk about is something called a mosaic plot. And think of a mosaic plot as just a graphical representation of the relationships that we get. Now, mosaic plots, let me go back over here and kind of give you a preview of what these things are all about. Mosaic plots are actually kind of cool. What they do is they give us a representation of the expected, observed and expected. Well, actually, no, it gives us a graphical representation of the expected cell counts based on the area in a square. So that really cleared it up, didn't it? We'll always start out in a mosaic plot. okay, as a square. And the way that it partitions out the area, let's just start with the default, which would be that pretend those areas are the same. And let's say that we're looking again over Democrat, Republican, pro-life, and pro-choice. These equal sizes would indicate to us that the equal number of Democrat and Republicans who were pro-life and pro-choice in terms of our expected values or our model values. Okay, and that's probably not what we're going to get because of the wide discrepancy in the standardized residuals. We could get something like this. Across Democrat and Republican and pro-life and pro-choice. Now what this tells you obviously is that the expected values across choice are the same for Democrat and Republican, and the expected values across life are the same for the Democrat and Republican. But the interesting information we would get would be vertically comparing these, which says across Democrat and Republican that the difference in the percentage, if you will, or the frequencies who are pro-life versus pro-choice wins out with pro-life. Something that would look very similar to this, clearly, if we had something that looked like this. Same explanation exactly, except the obvious is flipped. The expected values for pro-choice clearly more but equal across Democrat and Republican than the two segments here, the two chunks here that are equal but far less for pro-life. We get in typically on mosaic plots. It doesn't turn out anywhere like any of these 1, 2, or 3. What we typically get, we get something that looks like this. We'll get something that divides it down, and we'll get something that looks like maybe something like this. And interpreting this is you see across pro-life that the expected is higher for Democrats than Republicans. For Democrats who are pro-life, the expected value is bigger than the expected for pro-life Republicans, and even these two segments here, because we're comparing all cells. The way I've drawn it is clearly larger. All right, so let's stop speaking generally, and let's just jump over and let me show you how we want to do these in R. And I think these things are kind of cool, but I'm kind of a geek though. So the way we'll do this is we'll create mosaic plot for both the full and the partial models. And it turns out that in the mass function, the reason we way back up here loaded this, there's something just called a mosaic plot function. And what I want to do is I want to use the male model full, and I want to go $fit. And guys, always put shade equal true because it gives you kind of some cool stuff. All right, so let's do that. And what'll pop open is a mosaic plot just across males. And what you can see here is you can see that if a cell or if a rectangle has a dashed line, then that tells us that our standardized residuals are negative, which tells you a standardized residual tells you that the difference in the observed cell count is less than what we would have expected it to be. If we get a cell or a rectangle that is not dashed, and it can be either white or light blue or dark blue. Dark blue, light blue, and white just tells the magnitude, but the dashed versus not dashed tells us whether the observed cell count is higher than the expected cell count, or whether the expected cell count is higher than the observed based on standard errors. Okay, so all this again is standard residuals where we take the difference and we divide out by the standard error. And in these models, the standard error is the square root of the expected cell count. So when I look at this, I see a discrepancy. First of all, when I look across Democrats and Republicans, you can see that the width of these bars, or I'm sorry, these rectangles, is more for Democrat than for Republican. And I look at the belief, I look across choice and pro-life. Well, I mean, what do we see here? We see, first of all, we get blue, which is a standardized residual greater than 4. So both of these cell counts right here, the observed cell count is far more, for lack of a better phrase, than we would have expected it to be under the null hypothesis, which said there's no relationship. So the expected cell count for those who were Democrat and pro-choice is more than we would have predicted it to be under no relationship. And again, we saw this in the standard chi-square, but now we're just getting a picture and we're examining this just across males. Okay. Now you're going to see something interesting happen when you do the mosaic plot. And what I want to do here, instead of the full interaction model, is I want to do the none and take a look at it. So what we're doing here is we're not including the interaction across party and belief, and we get what I would, well, I can't say what I would expect because I've worked through this. I know what the results actually turn out to be. But based on this, our first of all, none of the cells are what I would call significant. The standardized residuals aren't dashed, so it means all of the expected values are more than what we would. Let's see. The observed cell counts are more than the expected cell counts, and again, being white, none of them fell above 2, and probably not above 1.96. Now, what this is telling me is it seems there's something going on with the interaction. Just looking at comparing the pro-life, pro-choice across each without the interaction of the two isn't really giving us substantial information. So we're gonna play that out. Now let's do that. First thing I want to do is I want to come in and look at the summary of our male model, our full, and see what happens. Now you get a bunch of gibberish here, and but what I immediately go to is I come down here to the bottom where I get my statistics of my likelihood ratio and the Pearson chi-square test statistic, and notice that our test statistic have a value of 0 and our probabilities are equal to 1. Now typically when something like that happens in a non-saturated model, it means we've done something wrong, but in this situation it doesn't. Well, anyway, these things turn out to be non-significant, non-statistically significant. And if you'll recall, these are just the goodness of fit test that test whether our expected values from the model deviate from the observed data. So when we get a non-significant high-order interaction, guys, write this one down. This is huge, okay? In trying to understand this and make heads or tails about it. When we get a non-significant high-order interaction, it tells us that is a good fit. So you kind of have to change your mentality. We're typically looking for statistical significance. In this situation, we're not looking for statistical significance because statistical significance means that the next order interaction model or the next order model significantly changes in expressing the difference between the observed and the expected. So this is telling us that we have a good model. It's a good fit. In fact, it tells us that this is a perfect fit. A perfect fit means that the expected values are the same as the actual data. So there's no deviation. but that's not the terminal process. Now, the second thing that we're going to want to do here is we're going to want to examine the second model that drops the interaction. So what I want to do here is I want to do summary of, now what did we call that? Male model none, right? Yeah. And, okay, that's interesting. Again, all the gibberish here, that means stuff to us, but my eyes, go here. It's kind of like looking at a linear model where we get the coefficients of a multiple regression model. Our eyes are naturally drawn to the p-values, and it's no difference here. My eyes are naturally drawn to the p-values, and notice our test statistics are higher. Of course, when test statistics go up, p-values go down. And in this case, there was a drastic difference. Now, this model allowed the proportion of males who were Democrats, for example, or Republicans, to vary across conditions. In other words, it allowed an association between the party and beliefs. So what we have is we have a high test statistic with a low p-value, which tells us that this model deviated significantly from the data. Now that's just new terminology you've got to tattoo to your brain. A low p-value tells us that the model deviates significantly from the data. And again, coming full circle here, non-significance, our p-value that we have way up here tells us that we have a good model, a good fit. So guys will interpret here the saturated model, okay? Now, let's let me check something real quick. I don't want to get too far ahead of myself. I'll tell you what I want to do. I'm gonna go away. My notes are telling me to do something else, but I want to go back over here and make sure that that we're on board with some stuff. All right, gang. Usually when I deviate from my notes, it gets ugly. But I got some stuff I want to say before we get to this. Guys, first of all, in log linear analysis, what I want you to keep in mind, if we only have two variables only, party and belief, then stick with chi-square. They are easier to perform, they're easier to interpret, and they're just less confusing. There's just less going on. So what we're doing from here on out, this log linear analysis, is performed with 3 or more categorical variables. Now these things get really, really ugly when you get into 5 and so on, but it's actually doable. So guys, what we're doing here is we're working with 3 categorical variables. And again, this is gender, party, and belief. And what we have is we start out with our main effects. And guys, our main effects are just gender plus belief plus party. The next thing we'll want to look at is we'll want to look at the next order interaction. And in this situation, it would be our two-way interaction. And guys, our two-way interaction, our gender across belief, gender across party, and of course, party across belief. Our next interaction would be a three-way interaction. And guys, obviously this is gender across belief across party. Now guys, in our situation, we call this the highest order interaction. Now, you know, just kind of think ahead here. What if we had 4 variables? Which you will. All right, what if we had 4 variables? So first of all, we would have one main effect. And what would that be? You know, for categories, we call those A, B, C, and D. We would have 6 two-way effects. We would have 4 three-way effects. And we would have 1 four-way effect. All right. Now, the reason this is so important to point out is because this sets the stage for the process that I'm getting ready to illustrate to you. You know, in introduction form. Next video, we're going to go through a problem in total presentation. We're going to write up the results and so on and so forth. But I think it's important here that we take this kind of slowly, because this is not stuff that you see every day. So guys, what we're going to do, we'll always start with the highest order interaction. And we'll examine this. If it is not statistically significant, which it typically won't be, then we'll go to the next. We'll examine those. Guys, we keep looking and looking and looking, and the first time we find a the first time we find a significant result, we go to the previous interaction that we tested that was not statistically significant, and that's the model that we should present. That's the model that best describes our data. So, guys, in a nutshell, what we'll do here, the procedure. Number 1, start with your saturated model. Okay. Remove effects until the model becomes significant. The third thing, finally, once you find a significant model, go back to the previous non-significant model, and interpret it. All right, so guys, let's make it happen. All right, so guys, I want to set up first of all using what we've established before. Let's start over. So step number one is I need to create a contingency table. Look at a saturated model. Most likely this will be non-significant. Now you're probably thinking, what happens if it's significant? Then we got major issues. And I'll do an example of that. Not this video, not next video, but the video after. And then we'll start looking at next level interactions. And as long as we get non-significant models, we just keep going on. There's a chance that we could go all the way down to our main effects. And then there's a chance that we won't. So, guys, let's see what happens here. What's going on with gender and political party and stuff. All right, so I'm going to call this the contingency table. All right, so I'm going X tabs just like I did before, but I want belief plus gender plus party plus gender. I want my data equal the full data set. So let's just see what this, well, I just want to show you, I know what it's going to look like. Let me show you what's going to happen here. What happens here, whichever variable that we put last, it's going to examine the relationship, well, examine the observed cell counts, I should say, across whatever variable we put last. So let's say, for instance, there was some motivation for us to want to look at belief over gender, but we'd like to express the contingency tables across party, then we just put party last. Now, I'm going to call this the full model. Okay, now you should know what's going on here. We want to run the log linear model of belief plus party. I'm sorry. That would have given us the main effects. And I want my data to be the contingency table. All right, so you see what's going on here. This is going to give us the full model. All right, so let's go for it. We want to do a summary. Let's see what happens. Well, as we expected, or at least I expected, our full model is non-significant, which tells us we need to go on and start looking at the lower level interactions. Let's look at a mosaic plot. And the mosaic plot, I want to look at that across the full model, considering our fit, and shade equal true. Oh, that's not going to work. We have okay, forget that, guys. We can't do that. We got a three-way interaction going on. Oops. All right, guys. So forget I tried to do that. That was just crazy. So, guys, our full model here is non-significant, which says we have a perfect fit. So we want to proceed. Now, the next thing we're going to do is we're going to create another model. And I have no other thing to call this other than the next model. But what we want to do here is we want to look at the main effects, plus we want to look at the two-way interaction effects. So I want to go plus, plus, and I want to look at plus party across, well, let's keep this way, belief, plus party. I want to look at belief across gender. I want to look at party across gender. And did I forget anything? So I've got, I should have 3. So belief across party, belief across gender, and party. Okay, perfect. Now I want to look at a summary of the next model and see what I get. Now, in this situation, I have a likelihood ratio that's not statistically significant, and a Pearson is not statistically significant. So we're going to keep going. Okay. Now, what I'd like to do now is I'd like to look at, to show you something, I want to run an ANOVA. Because, guys, remember, the next step is to compare the change in the likelihood chi-square, what I talked about in the previous video. And we can do that by taking, looking at an ANOVA of our, the full model with the next model. Now, this is going to perform just a difference of means, if you will, across the test statistics. And what we end up getting, and notice the p-values match up here with model 1 and model 2, which is the same thing we got in the likelihood ratio, the p-value there. So, guys, we're gonna keep on going. So, gang, what we want to do now, let's go on up here. So this has got to be the final model. And our two-way interactions weren't statistically significant. So I need to get rid of those. And just look at the main effects, right? Have I got that right? Tilde belief. Yeah, perfect. All right, so let's check out the final model. And guys, in the final model, we can see that we get statistical significance. So that tells me that I need to run my ANOVA across the next model. These are kind of weird numbers, or weird names. And against the final model, and see what happens. And I do have statistical significance. Now, so guys, what it tells me from here is that I need to examine to remove the two-way interactions. And when I get down into my main effects, then I have statistical significance. Now, what does this tell us? This tells us that we need to examine the previous model to see where we have statistical significance. Now, what I'd like to do here is, what do I want to do? So we've got statistical significance in the change of the model between the two-way interactions, right? Yeah. All right, so what I'd like to do here is I'd just like to examine the two-way interactions. And I think this is going to become pretty clear when I do this. Okay. All right, so let's go back up and get, I see, okay, I got it going on now. Let's go back up and get the next model. And we'll call this the next model 2. But guys, I want to concentrate just on, I'm going to be careful here. The interaction. Yeah. Now, if I go summary of the next model 2, I get non-statistically significant, don't I? So let's take a look at summary of log linear model between belief and party. Yeah. And I don't get statistical significance. So let's look across belief and gender. I do get statistical significance. And let's look across party and gender. And I do get statistical significance. So let's step back and take a deep breath and let's think about what we did. The very first thing we did is we examined the saturated model. It was non-significant. That told me that I needed to go on to the next model and include all the main effects and all the two-way effects. When I ran this model, I got non-statistical significance as well. So that tells me that I need to go on to the next order interaction model, which was just examining the main effects. Well, when I look at that, I get statistical significance, which tells me that I need to return to the previous layer, the previous examination, which were the two-way interactions. Once I see that, and I would say, well, I've got to return to the previous step, that tells me that I need to examine the two-way interactions independent of the others. And you can see when I ran the next model again that I get non-statistical significance, which means I need to delve into that examination more. And what happened here makes total sense because of the way that I created the gender variable. The gender variable was created just by a random number generator. And so what's actually happening is the belief across party is not statistically significant But when I bring gender into this situation, I get statistical significance, both with party and belief. So guys, at the end of the day, what this is telling us is that we can throw gender out, and because gender is pretty much irrelevant in describing this relationship. So again, we go to the previous model, which is not statistically significant. We go on and examine our other two-way interactions here. But this model right here, the one that examined belief and party only, the last non-significant model that we ran into is the one we want to focus on. So guys, at the end of the day, notice gender is irrelevant. So we need to focus on the result just for belief and party. Now, something I'd like to do for you here is I'd like to look at the difference here. So let's look at the male table. This is not what I want to do. What I'd like to be able to do here is I'd like to be able to take a look at all right. Because I know what I want to do, I just don't know how to do it. Let's see. Well, I tell you what, I'm going to have to study a little bit on R. What I actually want to do is I want to run some chi-squares, but I want to run those just across belief and party, but I want to run those separately for male and female and show you something. I know what's going to happen when we take those across gender. We're going to see something kind of cool happen. But guys, I don't know how to do that. So I tell you what, I'm going to end this video. The next video, when I start it, I'll have it figured out. And plus the next video, we're going to go through a complete example and end up showing you how to write this stuff up and so on and so forth. So guys, my apologies. I don't remember how to do this at the end, but I'll figure it out. And that's what I'll start out with in the next video. All right, guys, take care.